Okay, so in this video, I want to go through the solutions to the pH and indicator questions that I gave you. So could you please have the questions open in front of you, because I'm going to be kind of, reverting to the questions saying about tables and data and that sort of thing. So have the questions in front of you, have your solutions in front of you, and then play the video, okay? Now, the first question there, it asks you to use equations to show that when dissolved in water, be careful, you must here have the HCl reacting in the presence of water, right? Otherwise, you're not going to get any marks. So when dissolved in water, so you have to have the H2O. Now, how is that going to behave? Well, it's going to behave as an acid, so it's going to donate a proton, and that proton then goes and combines with the water molecule to form your hydronium ion, H3O plus. And then what will you have left? You'll have your Cl minus left, okay? Then you're also asked to do the same thing there with the base, with the ammonia, NH3 acts as a Brunson-Lowry base. Again, when dissolved in water. So you had to have the water present in the equation. Now, what do bases do? According to Bronsted and Lowry, bases will accept a proton. So the proton this time goes from the water. So you end up on the other side then with your NH4 plus and OH minus, because the water molecule has lost the proton. Now, the next part of that A then says HCl has a weak conjugate base. Explain why HCl has a weak conjugate base. So just go up here now again to the top for a second. HCl is a strong acid, okay? If it's a strong acid, what does it mean? Our definition of a strong acid is that it's a good proton donor, okay? So it's going to dissociate fully, actually would be Arrhenius' definition, wouldn't it, of a strong acid? HCl dissociates fully, 99.9% dissociation. So nearly all, nearly 100% of the molecules will dissociate. So the equilibrium lies very much over here to the right-hand side. This reaction favors the forward equation. Look at the arrow. The arrow is showing you that this is going to completion. So it's all being driven over to the right. Equilibrium lies very much to the right-hand side. So does this conjugate base here have much of a tendency to accept the proton and go back over to the left? No. So you'll explain that the Cl minus ion is the conjugate base, and it has a very, very little tendency. It's a weak base, very little tendency to accept a proton and go back over. Why? Because the equilibrium lies very much to the right hand side, or you could say something like the forward reaction is favoured greatly. Okay? Now, the second one then, you're asked to explain how this is actually quite a good, they use the word strong, don't they? Why this is a strong conjugate acid, okay? Now, this is a weak base, okay? So if it's a weak base, what does it mean if it's a weak base again? Well, it means that it has a poor tendency to accept protons. It's a poor proton acceptor, or it does not fully dissociate. Remember, that was your Arrhenius' one. So if it's a poor proton acceptor, then this time the equilibrium lies very much to the left-hand side, or you could say that the reverse reaction is favoured. So what will you ask yourself? Is there much of a tendency of this NH4 plus to actually donate the proton and go back? Yes, there is. So you're going to say that the NH4 plus is a strong acid. It has a good tendency to donate a proton and to drive it back over to the left-hand side. Equilibrium lies very much to the left would be another way of putting that. Okay, so that was part A. Part B of that question now then says, it gives you the dissociation of water. Now they're using the H3O plus and the OH minus. It doesn't matter. I was using just the one. Do you remember when I was doing it? I was saying just H plus and OH minus. It doesn't matter. They're using the top one. Don't let that confuse you. H3O plus, you're just taking it that it's the same as the hydrogen ion concentration. Okay? Now, it says write the self-ionization constant, or the Kw expression. That's the first thing that you were asked to do in part B. So we would have written H plus and OH minus. You got your 3 marks for that. It must be square brackets though. You're not going to get 3 marks if you don't have square brackets. Alternatively, you could write H3O plus and OH minus, whichever got you the marks there. Now, part 2 says, are the data in the table consistent with self-ionization of water being exo or endothermic process? Now, if I was you, what I would do there is, I'll just clear that there for a second. What I would do there is I would say to myself, right, okay, what do you notice from the data anyway? Well, you can see there, as the temperature increases, then the value for Kw also increases, right? So from the table, I saw that now. So you must have the table in front of you. Going from 0 to 60, an increase in temperature. What are happening to the numbers? The value of Kw, that's also increasing. So you're going to say to yourself, well, what's the stress? What does the reaction want according to Le Chatelierre, and how is the reaction going to achieve that then? So we'll use those kind of, we'll use those prompts for ourselves. Now, the stress is that you increase the temperature, okay? So the temperature is increased, that's the stress. Now, what happens as a result of that increase in temperature? Well, as a result of increasing the temperature, the Kw value increases, okay? And what does that actually mean? Well, if the Kw value increases, that means that there are more protons and more OH minuses. In other words, you are favouring the forward reaction, okay? You are producing ions. The water is ionizing into H plus and OH minus. Self-ionization of water, H plus and OH minus. So we are favouring the forward reaction by increasing the temperature, okay? So the forward reaction is favoured as we increase the temperature. How do I know that? Because my value for Kw is increasing, which tells me there are more ions present. Now, if the forward reaction is being favoured as a result of an increase in temperature, then that forward reaction must be endothermic, okay? So if the stress is that you're increasing the temperature, the reaction will want to decrease the temperature. And how is this particular reaction decreasing temperature? Favouring the forward reaction. So the forward reaction must be endothermic. Okay, so you'd have to explain that in your answer. So you'd say, so obviously is the data consistent with self-ionization of water being exothermic or endothermic? Your answer is endothermic. And justifying your answer, a sentence like, the forward reaction is favoured as the temperature is increased. Therefore, the forward reaction must be endothermic. That would be perfect. Okay? Now, part 3 then of that was plotting a graph. Now, it doesn't tell you about axes or anything like that, but generally speaking, the independent variable is the thing that you're changing. Now, you are changing the temperature here from 0 to 60, okay? And what you would be putting up here then would be your Kw values. And you plot your graph, okay? Now, it didn't specify in the marking scheme, so if you had it the other way around, but generally what you change goes on the X, and what you're kind of measuring then goes on the Y. Now, it asks you to use your graph to predict the value of Kw. Now, when I used my graph to predict the value of Kw, I was getting a Kw value of 2.1 by 10 to the minus 14. You might have gotten something different now, lads, but and there was a range accepted in the marking scheme. So that's what I got for my Kw value. How did I get that, of course? Well, on my temperature axis, I found 37 degrees. I went up, where did my graph? I went across and I read off my Kw value, okay? Now, for part 5 then, I was asked to use this Kw value to predict the hydrogen ion concentration of pure water at 37 degrees, okay? Now, the Kw that I got, as I said, from my graph was 2.1 by 10 to the minus 14. Kw is the hydrogen ion concentration times the OH minus ion concentration. Now, some of you might have had H3O plus here. It's the same thing, so whatever, okay? Now, because it's pure water, the minute you're reading pure water, you are straight away thinking what's inside the bracket is the same. So I can rewrite that now so as hydrogen ion concentration to be squared, and that does equal 2.1 by 10 to the minus 14. So what's the hydrogen ion concentration itself? I have to square root that. And what did I get when I square rooted that? I got 1.44 by 10 to the minus 7. So that's my hydrogen ion concentration. Okay. Now there was a range of values. Accepted there. Let me just look for it now again. Oh yeah, the values that were accepted there, anything between 1.44 10 to the minus 7, which is what I got, and 1.59 by 10 to the minus 7. So if your value is within that range, then it's absolutely perfect. Okay. Now, the next thing you were asked to do then after that was, so you have the hydrogen ion concentrations. This is the last part now. Sorry, now I'm just trying to get it right. So, VI, okay, the last part of the question was, if the pH of pure water is close to 6.77, so that's the pH it says, and one of the temperatures in the table, find by calculation this temperature. Now lads, the minute I tried to make this point as well when I was making the videos earlier, but the minute you are given the pH, straight away you can use your pH formula to calculate hydrogen ion concentration. So if you can try and get into your head, the minute I'm told the pH of something, I can use my pH formula to get the hydrogen ion concentration. So that's what I'm going to do. I'm going to go anti-log minus 6.77, and that gives me a hydrogen ion concentration of 1.69 by 10 to the minus 7. Okay, so that's my hydrogen ion concentration. Okay, now what I'm asked to do, now I have been given KW values in the table. Okay, now what's KW again, remind yourself? Well, KW is the hydrogen ion concentration times the OH minus ion concentration. But this is pure water, so what's inside the bracket is the same here. So I can rewrite hydrogen ion concentration to be squared. Okay, this is my hydrogen ion concentration. All right, so when you do the square root of that multiplied by itself, if you like, then you're going to get your value. What was my value? 2.85, by 10 to the minus 14 is my KW then. Okay, so just to repeat there now. Sometimes students find these exam questions very difficult, okay? And you can find them very difficult. Some of them are very hard, right? But you're just going to have to try and practice them and get into them as best you can. The minute I was told there that the pH of pure water was 6.77, I thought to myself, I can get the hydrogen ion concentration. Anti-log minus 6.77 gives me the hydrogen ion concentration of 1.69 by 10 to the minus 7, okay? I then, in the table, I need to match, a KW value. At the moment, I've only got H plus concentration. KW for pure water, okay, is the hydrogen ion concentration to be squared. So when I square that, then I got my 2.85 by 10 to the minus 14. Now I have to go to the table in the question. What temperature, okay, has the closest KW value to 2.85 by 10 to the minus 14, and it's 40 degrees when you read it off the table, okay?